Well, hello again, everyone. I hope everyone had a good break. Today we're going to be looking at a couple of different types of scales and introducing you to the concepts of sets and set class analysis. So, if you look at the very first idea up here, I'm going to make this a little larger so we can see it here. If you look at the very first idea, you see that this is what? That's right, fully diminished seventh chord. The B double flat is written in harmonically as an A, and that's fine. The quality of a fully diminished seventh chord is such that it is symmetrical in nature. Symmetrical in nature because it is the same distance or the same pattern of distance as intervals between each chord factor. Minor third, and harmonic minor third up to C, and so forth and so on. Now, think about the idea of symmetry. What constructions can you think of are perfectly symmetrical? Well, here's an example of one. The chromatic scale is symmetrical because the distance between each factor of the scale is exactly the same, a half step. The whole tone scale, which we've mentioned in passing before, which we might look at a little later on, is also symmetrical in nature because it has the same interval. If you look at the what's marked as bar 4 here, this is a minor pentatonic scale. It too is symmetrical because you have a minor third from E to G, then two major seconds, G to A, A to B, and then another minor third. So it has the same pattern all the way around. So this would be an example of a symmetrical scale as well. But let's revisit our diminished triad here, or diminished seventh chord. We can turn this into a scale by adding some pitches, filling in the gaps between the minor thirds here, the note bounded by the minor third. My question to you is then, is there a way to divide this evenly, such that we can divide a half step or a whole step into two equal half steps? Is there a way to divide a minor third equally? The answer is no, not at least within Western systems. If we're working at microtones, you can certainly divide it into two 3/4 tone segments, but we don't have that luxury. So there are a couple different ways we can look at things. If we take the notes of the scale again, and think about the interval of the minor third. I'm going to go ahead and copy that into the next measure so we have that ready here. Think about the interval of a minor third. How can that be divided? You can't divide it perfectly equally, but you can divide it into two uneven intervals. What are those? A major second and a minor second. So it depends on what order you choose to do that. So if we started with a minor second, so say C, D flat here, there's a minor second there, and then a major second between D flat and E flat. So what's a minor second above E flat? If we're going to start this process, minor major, well, let's go with minor major. Minor second above E flat would be E natural or F flat, which naturally creates the whole step, the major second, to G flat. Half step above G flat would be A double flat. For convenience, we'll write it as G natural. So a half step, whole step, and then a half step above B flat would be, A would be B flat, and finish that out with the whole step to C. So as you can see here, we're alternating half steps and whole steps. Now we can do the same thing with this next collection. But instead of starting with a half step, we'll start with a whole step. What is a whole step above C? That's right, the answer is D. Then we have a whole step followed by a half step. Now what's a half step above, a whole step above E flat? It's F, that's correct. Then a whole step above G flat would be A flat, And the whole step above A would be B, and then C to finish it out. Now, if we look at this particular setup, we're still alternating whole steps and half steps, but you'll notice we're doing them in a different order here. Instead of half, whole, it's whole, half, whole, half. Now, one of the things we'll do in class is we'll generate all of these possible scales that can be created from diminished seventh chords. You might be surprised at how few there are. You'll also notice that they always contain the same notes present, the C, E flat, G flat, A natural. It's our fully diminished seventh chord, and it's going to be present in either of these. How many individual pitches are there before you repeat yourself? 8. So these are what we call octatonic collections. In class, we'll drill down a little more and talk about all of the possible octatonic collections. So octatonic collections are, by their very nature, symmetrical because they set a pattern and repeat it. In this case, either half whole or whole half, depending on where you're going. And we'll talk about the organization and taxonomy of octatonic collections. Let's take a look at this minor pentatonic here. Now, that too is symmetrical, as we talked about, but I want to mention a couple of things that are present here. You can also think of any collection of pitches as a set, and that's going to be the generic term we have right now for collection of pitch, a set. A set is some kind of collection of pitches that has been segmented out in some way. We're going to talk an awful lot in class about segmentation. And so what we've done here is we've taken of, say, the 12 possible chromatic pitches, we've segmented out these 5. So from the 12 total pitches that are available, pitch classes that are available to us, we have way more than 12 pitches, but we only have 12 pitch classes, as you know. We've selected these 5. We have segmented out these 5 pitches from what we can call the total collection of all 12 pitch classes, or another term for that is aggregate. And we'll be exploring that a little more as we go along as well. But these 5 pitches form a set. And we'll talk about some of the notational issues as we go along here, but how can we organize this? Well, we talked about it as a minor pentatonic collection. You know, E, G, A, B, D. If you're thinking fixed do, or if you want to use C as your do, this would be mi, sol, la, ti, re. E, G, A, B, D. Various ways we can organize this. But owing to language barriers, different solfege systems, perhaps it would be best if we were a little more abstract about it. So one of the things we can do is we can use integer notation. Now with integer notation, you simply say let C equals 0. And then you look at a clock face to help you out with this. If C equals 0, the next stop on the clock is 1. What pitch do you think is at 1? C sharp or D flat? So C is 0. C sharp or D flat is 1. What's at 2? That's right, D. Then you go just basically up the chromatic scale. It's a little different than the circle of fifths. But the idea of integer notation here, so C equals 0, C sharp or D flat is 1, D is 2, D sharp or E flat is 3, so forth and so on. So we can convert these into integer notation. So E would be 4, and we always start with C at 0, not 1. G would be 7. A would be 9. B would be 11. And you can use a capital or a lowercase e for 11 here. The reason we use letters for 10 and 11 is because they have 2 numbers, and if you're in certain systems, it's awfully hard to keep track of should there be a comma there or not. So there's no confusion. We'll use T for 10 and E for 11, and then D here, of course, is 2. So this set, as it's expressed, is 4, 7, 9, 11, 2. One of the things we'll do as we go along throughout class is talk about how we can order these sets. We're going to move away from unordered sets into ordered sets, and We're going to try to find what's called the prime form of the set in the normal order of the set. And there are various operations, but I don't want to give the ball game away just yet. The only other thing I really want to introduce at this point is the idea that not only is this a set, these 5 pitches make up a set, and any 5-note set is going to be called a pentachord. There are terms, a 2-note set is a dyad, a 3-note set is a triad, and then from 4 to 11, we have other terms. A tetrachord for 4, pentachord for 5, hexachord for 6. Hexachords become very important. Hepta or septachord, I think usually heptachord is what's used for 7. Octachord for 8, just like we have the Octatonic collection. Nonachord for 9. Decachord for 10. And undecachord for 11. And then for 12, we just say, well, that's the aggregate. That's everything. So we have sets of varying sizes, but I can pull out certain pitches from that. If I pulled out G, B, and D, the G major triad, what we have here is a collection that is present in this one, but is not the entirety of it. So we can say that the G major triad here, 792 GBD Sol Ti Re, is a subset of this collection. And if you put, if you pull a subset out, we can talk about both the literal subset, which is what this is, and what's called the abstract subset, which will be what this is after we've reduced it down to its component intervals and found its prime form, etc. But we'll get inside that later. I don't want to scare you away right now. There are some other terms we'll talk about in class, things like complement and superset. And we'll get into those a little later on. But I just wanted to introduce these concepts to you now, because chapters 33 and 34 and 35 are a lot of fun. There is going to be math. You are going to be required to count to 12. I think you're capable of that, especially since you'll be starting on 0. So you only have to actually make it as far as 11. I think we're all in college now. We can probably handle counting to 11. So if you have any questions, please feel free to find me. I'm happy to discuss this with you anytime. Thanks for watching as always, and have a great day.